right. Number one gives us a scenario where we have a parking lot that's in the shape of a parallelogram. And it gives you the lengths of two of the adjacent sides, which are 70 meters and 100 meters. And the angle between those two sides is 70 degrees. And we want to find the length of each diagonal in this parallelogram. So hopefully you know what a parallelogram looks like. Quadrilateral that has opposite sides parallel. And we know that the adjacent sides, which would be two sides next to each other, are 70 and 100. Then the angle between those two sides is 70 degrees. And we want the length of each diagonal. So we'll start off by identifying the length of this diagonal. And you'll notice that when we draw in that diagonal, we actually have a triangle here. It's not a right triangle, but that doesn't, we're not needed that. We have the law of sines and the law of cosines that allow us to find missing sides and angles of a triangle. In this case, we're trying to find one side of that triangle. And should we use the law of sines or should we use the law of cosines? We have to use the law of cosines because we don't have an angle-side ratio at all. So we're going to use the law of cosines. Because we're trying to find x, that's going to go on one end of the equation. And of course, the angle opposite x, which is 70 degrees, will go on the other end of the equation. And then in between, we're just going to fill in 100 squared plus 70 squared minus 2 times 70 times 100 times the cosine of 70. And then from there, we just put all this into the calculator and evaluate. So we'll type all that in, just as one long line, and then take the square root of it. And what's one diagonal? 100.57. All right, everybody in agreement with that? And our units are meters, so we want to make sure we label that. And then we'll work on the other diagonal because I believe it wants us to find the length of each diagonal. So that diagonal would be this right here. That one Y. So if we're working with this triangle, what all do you know about this triangle?
Q of the angles. I don't know anything about it.
It would. How do you know that?
Because they have people when they be on
They do, and the reason for that is when we take two parallel lines and we cut it by a transversal, then same side interior angles are supplementary. That's a theorem that you learned back in geometry. And in this case, we have parallel line, cut by a transversal. So those same side interior angles are supplementary. So if this is 70, and this one's 110. And so now we do know, that angle is 110. This side, in a parallelogram, not only are these sides that are opposite parallel, but they're also going to be congruent. And so this side is 70, so we'll have this side as 100. So now we'll just set up y squared, which is the diagonal that we're trying to find. On the other end is going to be the cosine of the angle that we have across from that side. And then we fill in the middle, which really is going to look the same as the one previously. And then we'll evaluate all that, take the square root, and what do you get for this side? Meters. All right. So there are your two diagonals. Everybody good on number one? angle's not the same? Well, you can tell by looking at this that one's got to be shorter than the other. And then one of these angles, I mean, this side is across from a smaller angle than this one is. Okay. Now, if it were a rectangle, then now those diagonals would be congruent. Okay? Or if it were a square, they'd be congruent. But they're a parallelogram, because of that angle, it's going to be a little bit. All right, number 2 says the boat leaves the buoy heading 30 degrees east of south and traveling 50 miles an hour. And then another boat leaves the same buoy heading 50 degrees east of north, traveling 30 miles an hour. I probably meant to tell you that the second boat was leaving at a different time than the first boat based on this question. How far apart are the two boats? 3 hours after the second boat leaves, but we didn't say that, so we're just going to assume that they both leave at the same time. And we've done problems where one leaves at a different time than the other, and we know how to handle that, but we'll just assume in this case that both of these boats are leaving this buoy at the same time. So both boats have been traveling for 3 hours. The first one is heading 30 degrees east of south. So, looking at these cardinal directions, instead of heading due south, the boat turned 30 degrees towards the east. So the boat was actually heading in this direction, and this angle here would be 30 degrees because the boat turned 30 degrees towards the east of south. And then if that boat's been traveling for 3 hours at 50 miles an hour, how far has it gone? 150 miles. The other boat is left and is heading 50 degrees east of north. So instead of heading due north, then the boat actually turned 50 degrees towards the east. It's traveling 30 miles an hour, and it's been traveling for 3 hours, so how long has that boat gone? Okay? And then what we're looking for is the distance between these two boats. Okay, so here is the triangle that we're going to make use of. We know two sides of that triangle are 90 and 150. And we're going to be able to find this angle because, if we, that straight line segment there would be 180 degrees. And we know part of it's 50, another part of it's 30, then what's remaining? 100 degrees. And we're trying to find this distance between the two boats. So law of sines or law of cosines? Law of cosines again. Okay, so the side that we're trying to find will go on one end of the equation. On the opposite end of the equation is going to be the cosine of the angle across from that side. And then we'll fill in the middle. It's going to be 90 squared plus 150 squared minus 2 times 90 times 150 times the cosine of 100 degrees. And then we get to input all that in the calculator and take the square root of it. And what do you get for that distance between those boats?
I got 187.852.
That's 8.852 miles. Our units. Don't forget to include your units.
Radius. 187.852.
If it was to say, I don't know if it would ever say this, but if it was to say south of east, would it go like the other side?
Yeah, typically we always start from north and south and then move towards the east or west. But if it ever read that way, south of east, then you would say instead of going east, we're going to turn towards the south, and now that angle would be there. Yeah. But for some reason, when we give these directions, it seems like we always say from due north or due south, turn one way or the other. Okay, the next one. Everybody good on number 2? All right, numbers 3, 4, and 5, I've labeled them as the ambiguous case. They're not all ambiguous case problems, but when we get to one, I'm going to kind of guide you through what that means when I say that it's an ambiguous case. But this first one, if I'm not mistaken, it's not an ambiguous case. It tells us to solve triangle PJA. And we don't know what that triangle looks like exactly, but we do have some information about it. We know that angle P is 57 degrees. We know that side J, which is going to be across from angle J, is 9. And then side P, which is across from angle P, is 5. And we want to solve this triangle, which means that we've got to find everything that's missing. And what else is missing in this triangle? Right, angle J, angle A, and side A. And do you want to use the law of sines or the law of cosines? Well, we can only use the law of sines. So either the law of sines or the law of cosines will work when we're given 3 pieces of information. So we got to make a decision. In this case, the law of sines, because we have an angle-side ratio. So we have the sine of 57 degrees over the side opposite equals the sine of, which angle are we going to use? J, because we're working with side J, which is 9. Now this is working. All right, we're going to cross multiply, so that's going to be 9 times the sine of 57 degrees equals 5 times the sine of J. We'll do 9 times the sine of 57 degrees, and then we'll divide by 5, and what do we get? 1.509?
Now we're screwed. Now we'll plug into the side.
Right, and so when we try to use sine inverse, we get an undefined value or a domain error. So we talked about yesterday, we had a problem like this yesterday. We're going to say that this is not possible. And the reason it's not possible is what this is saying in words is find the angle whose sine value is 1.509. In other words, find the angle on the unit circle where the y-coordinate is 1.509. But on the unit circle, the biggest y-coordinate we have is 1. Okay? So we can never have a sine value or a cosine value that's bigger than 1 or less than -1. It's not possible. And so that means that we can't find the angle. That means there's no triangle that exists.
Big triangle.
Right? So there's no triangle that fits this criteria. Okay? It's not possible. And so that's not really an ambiguous case problem. Okay? What does the word ambiguous mean? Yeah, like a mystery, or it's uncertain, or we can't distinguish between answers. That's what ambiguous means. If it was unambiguous, that means there's one answer. Well, this is not an ambiguous case or an ambiguous answer, because the answer is there is no answer. It's no triangle exists that will fit those conditions. But we're going to see problems here in just a second where there's actually multiple triangles that will fit certain information. And in those cases, it's going to be referred to as an ambiguous case problem. So let's see if number 4 is one of those. It says to solve triangle RST, where angle R is 63 degrees, side R is 76.3, and side S is 23.4. Okay? Again, if we're going to solve this triangle, then we're going to have to find angle S, we're going to have to find angle T, and we're going to have to find side T. And we'll do the law of sines again, because we have an angle and its opposite side. And then since we're given 23.4, then we're going to find the sine of S. That's the side that's across from the given side. So we cross multiply 23.4 times the sine of 63 equals 76.3 times the sine of S. We do 23.4 times the sine of 63 degrees, and then we'll divide it by 76.3, and what do you get for the sine of S? 0.273. Okay, everybody good to this point? And we've done problems like this before, so not surprising to this point. But one thing that you've really got to pay attention to, again, understand what this is telling you or asking you to find. You're solving this equation. You're going to use the inverse sine, but what you're really finding is the angle on the unit circle where the y-coordinate is positive 0.273. Okay? So think about your unit circle. Where on the unit circle is our y-coordinate positive? In both the first quadrants and the second quadrant, right? And this is important, and this is where the ambiguous case comes in. When we're trying to find a sine, an angle, using inverse sine, and it's equal to a positive value, that could occur in multiple quadrants. Okay? Now, go ahead and put in inverse sine of 0.273 on your calculator. It tells you 15.856.
Yeah, I got
8.42.
Well, it depends on whether you use the full decimal or you round it. Who used the full decimal?
8.273.
If you use the full decimal, not just 0.273, what do you get?
8.43.
Well, I still got the straight.
You got it. I thought you were saying.
I got 8.6.
8.43.
But it's the same whole number.
Oh, I was like 8. I was like,
If you did inverse sine of 0.273, then you're going to get an answer. If you did inverse sine of second answer, you're going to get a better answer.
yeah, I got it.
And that's the better answer?
No, that's the worst.
No, that's the worst.
That's the 0.273 answer.
So the better answer when you do 5.6. Okay. That's really what we would prefer because that's the more accurate answer. If you use the full decimal, then you get the more accurate answer. Okay? But here's where the ambiguous case comes in. You'll notice we said that there's two places on the unit circle where the y-coordinate is positive, in the first quadrant and in the second quadrant. Okay? Your calculator only tells you one of those two answers. It's only programmed, for good reason, to tell you one of those two answers. It's automatically going to tell you the answer in the first quadrant. But there is a second answer that's possible out there. It's this answer over here in the second quadrant. How do you think we could go about finding what that second answer might be?
Something to do with 180 or
Something to do with 180.
okay. Maybe 180 minus.
Yeah, 180 minus 15.856. That's going to give us this answer over here in the second quadrant because it's going to use that reference angle to find the answer in the second quadrant. So what is the answer over here in the second quadrant? 180 minus 15.856. 164.144. So it might look like there are two possible answers for angle S. And we have the answer in the first quadrant, because that's an angle where the y-coordinate is 0.273. But there's also an angle in the second quadrant where the y-coordinate is positive 0.273. And we get that by saying 180 minus 15.856. But for this particular triangle, this can't be. Why not? Yeah, if we match up with this angle that's given, we're way over 180 degrees, right? So we can rule that one out. But it won't always work that way. Sometimes we'll come up with an angle that still would allow us to have something left over. And in that case, that's called the ambiguous case, because you'll have two different triangles that fit the criteria that are given. Okay?
don't you always have two values then?
Yep.
When you're doing sine?
Yep. If we're when we use sine to find an angle, there's always going to be two possible answers.
We're just,
Because we've never done it before. I made sure to never make it
Got
happen.
extraneous solutions now.
so like on the test, like you want us to find
They only have to be law signs.
Only happens when you use law of sines to find an angle. Right. And if on the test, you got a test for both of them. You got to see, does that second one, is it a possibility? And at number 5, it's going to work. So we're going to get to that example in just a second. Okay.
can the first one?
Yeah, in this case, the second angle didn't work because it would take us over 180. But if it doesn't take us over 180, then we got to list both answers. Okay? Because it means there'd be two triangles that would fit the criteria that are given.
So you add the second angle to the 63.
Right.
Goes over this
If it goes over 180, then you don't have to worry about it. Okay? In this case, we don't have to worry about it. All right, let's finish this one off. We're only going to make use of the 15.856. Okay? Now, I can easily find angle T because I've got two angles of the triangle. Subtract that from 180, what's left? All right, 101.144. Okay? There's angle T. We still got to find side T. But now that I know what angle T is, then I'm going to be able to use the law of sines again. And that will be the sine of 63 degrees over 76.3 equals the sine of T, which I've just found to be 101.144 over side T. And then we'll cross multiply. In this case, I don't have to worry about two answers. I'm not finding an angle, I'm only finding a side. So when we cross multiply, it'll be T times the sine of 63 degrees equals 76.3 times the sine of 101.144. And then we'll type all that in, divide by the sine of 63 degrees, and what do you get for this third side? Say again. 34? 84. Point 01. Sorry, perfect. And so there's that third side. I go with that. Okay, but number 5 is going to be an example of the ambiguous case, where we're going to have two possible answers. So it says, solve triangle XYZ. And angle X is 38 degrees, side Y is 45, and then side X is 42. We need to find angle Y, we need to find angle Z, and we need to find side Z. We're going to use the law of sines because we have an angle side ratio. The other piece of information we're given is 45, which is side Y. So we're going to be looking for angle Y. We're going to cross multiply. And then we're going to ultimately get sine of Y. And it's going to be 45 times the sine of 38 divided by 42. What's the decimal?
0.669.
0.659. 45 times the sine of 38 and then divide by 42. Okay. Now, again, we're going to pay attention here. Notice we're about to use inverse sine to find an angle. And what this is asking for is the angle on the unit circle where the y coordinate is positive And we know that could happen in the first or second quadrant. Why does this not happen with cosine? What quadrants is cosine positive in? First and fourth. Well, what are our angles down there in the fourth quadrant? 270 to 360. That can't be part of a triangle anyway, right? It's only because that sine is positive in the first and second that we got to pay attention, okay? Because we could get, acute angles or obtuse angles for a triangle. We can't get any angles over 180, so anything in the third and fourth quadrants doesn't matter. Our calculator is only going to give us one answer. Okay? There's a reason why it only gives us one answer. We'll talk about that after Thanksgiving, but it's only going to give us the one answer in the first quadrant. What's the inverse sine of 0.659? Say it one more time.
41.224.
Okay. There's one answer for angle Y. And the other one is what? 138.776. Okay. So there's the other possibility. 138.776. Okay. So what we've got to see is, will this second angle still leave us something for that third angle? Yes. And it does. And that means both of those are valid answers. Okay? And we got to keep both of them. The problem now is, if you've got two answers for Y, then you're going to have two answers for Z. If you've got two answers for Z, then you're going to have two answers for side Z. Because really what we have are two different triangles that meet these initial criteria that are given. And we've got to find the remaining sides and angles for each triangle. Okay? So let's go to angle Z. This part's not so bad. If angle Y is 41.224, add that to 38 and then subtract it from 180. And what would the third angle be?
$100.776.
But if angle Y is 138.776, you're going to add that to 38, subtract it from 180, and what's left?
3.224.
Okay. So you see, we could have angle Z could either be an obtuse angle or it could be a really small acute angle. Okay. Triangles are going to be different, but they're still going to meet the initial criteria that are given. Okay. Here's the crappy part. You got to find angle Z. Well, to find side Z. Find side Z. So we got to do the law of sines. But unfortunately, we're going to have to do the law of sines twice. Once with an angle of 100.776. And then again with an angle of 3.224. So you're going to get two different answers for side Z. Okay, from each of those law of sines problems. And I'll trust you can figure all that out on your own, but you'll notice what we have here, this is an example of the ambiguous case because what's happened is we've gone through all this work and we ended up with two possible and both valid answers for angle Y, which means there's going to be two valid angles for Z, which means there's going to be two sides, two values for side Z, both of which are going to fit those criteria. So you have two different triangles that have angle X at 38 degrees and those two sides at 42 and 45. I'll trust y'all. All right, any questions? Everybody okay? All right, you had some homework last night, but let's hold off on going over that until tomorrow. And that way, if you didn't quite get it all done, then you can finish that all tonight. And we'll make that part of our review for our test on Friday. Okay? So I want to go ahead and make sure we get the lesson in today so that you can do that homework tonight. And then tomorrow we'll go over the law of cosines homework, the homework from tonight, and then any questions you have from your study. Okay?
I got that armor break. I'm going to be like,
Okay.
I'm going to take one of those.
Be sure. I'm also recording a lesson, and I'll put that on.
See the best coach. Be like, hey, I'm doing an advanced class, and then come back and look at stuff.
Yes. 6.
Area
I was just trying to be a smart. My chicken nugget is busy. Oh, my chicken nugget is busy.
All right, so here's what our last thing that we're going to cover in this unit is trigonometric formulas. And these are really fairly easy because it is simply a formula and you just got to plug in the given information. Okay, so we should be able to run through these fairly quickly. We have 3 different formulas that we'll talk about today. One is Heron's formula, one is the area of a sector, another one is the length of an arc. Okay? And Heron's formula, I will not make you memorize that. Okay? That one is a very specific and not often used formula, but it is can be valuable at times. The other 2, the length of an arc and the area of the sector, those are formulas that I am going to have you memorize because we do make use of those a good bit. But let's just go through and see what these formulas are, and then we'll solve some problems with each of them. First formula is known as Heron's formula. And I'll give you a second to put this in your notes. Oops.
That would suck.
What's the name at the bottom?
I'll explain.
Teachers, please pardon the interruption. Will all juniors with honor roll passes report to the cafeteria? All junior students with honor roll passes report to the cafeteria.
It's been a pleasure. I'll do that.
All right, this formula is named after a mathematician, Heron, who came up with this formula. What he recognized is that oftentimes when we are given a triangle and we're asked to find the area of that triangle, we're not able to find all the information that we need. For example, let's say we're given a triangle, and it's not a right triangle, but we're told, maybe this side is 12, this side is 10, this side is 14 or something. And when we try and find the area of a triangle, what we'll need is the base, which we'll call 12 in this case, but we're also going to need the height. And we can't find that. Right? We don't have any method of finding the height of that triangle. If we knew this angle, then we might be able to find, or we would be able to find the height, and then ultimately the area. But, from what's given to us right here, there's no way for us to find the area of that triangle simply because we don't know what the height is, and the area of the triangle is 1/2 base times height. So Heron developed another formula or another method for finding the area of the triangle when you're given all 3 sides of that triangle. And if we're only given 3 sides and not the height or any angles, then we need another method. And he developed this formula here, and it's the square root of S, which is the semi-perimeter, times the semi-perimeter minus each side of that triangle. Okay? So that's what this S down here stands for. The semi-perimeter is half the perimeter. So 1/2 the sum of the 3 sides. So you're going to add the 3 sides together, take half of that, and then that's going to be S, and then you're going to find the difference between S and each side, multiply those together, and take the square root. Once you get the process down, it's a really easy formula to use. It's just as long as you have three sides of that triangle. So let's look at an example of it. All right, it says, let's say we want to find the area of a triangle that has sides of length 7, 11, and 17 meters. So it's a triangle with sides 7, 11, and 17. So the area of this triangle is going to be the square root of S times the difference between S and each side. So S is 1/2 times the perimeter. So what's 7 plus 17 plus 11? 35, and half of 35 is 17.5. So that's S. And then we're going to multiply that times the semi-perimeter minus each side. So 17.5 minus 7 would be 10.5. 17.5 minus 11 would be 6.5. 17.5 minus 17 would be 1/2. So we'll do the square root of 17.5 times 10.5 times 6.5 times 0.5. And what do you get? 24.47. And our units in this case would be square meters because we're talking about here. But that's how we go about finding the area of any triangle if we're given three sides and we're not able to find the height of that triangle. And we just find the semi-perimeter, and then it's the semi-perimeter times the difference between the semi-perimeter and each side, and then you take the square root of it. Not too bad.
And it's not really that hard.
No, it really wouldn't be. I'll give it to you, but it really won't be that bad a performance. All right, number 2, a businessman wishes to buy a triangular lot in a busy downtown location. And the lot frontages on the 3 adjacent streets are given, and he wants to know what is the area of the lot. So, now again, this lot just happens to be shaped like a triangle. As it just runs through these, these 3 streets, kind of run alongside this lot.
Don't make fun of it. Just Smith's lot. Jeez. Did you pay for it? Have they changed you at a lot?
It's like a triangle and a traffic circle.
I knew Coach Jackson was looking
So here is this lot that he wants to purchase, and the side lengths for this lot are 125, 280, and 350. And he wants to know what's going to be the area of that lot. So probably would want to build a building on it or something, and wants to know what's the area so that he can determine how much of space they leave for parking, and then how much what could be the area of that building, the base of the building, foundation. So to find the area of it, we'll start by finding the semi-perimeter, which is going to be 1/2 times 125 plus 280 plus 315. And what do you get for that semi-perimeter? 360. So there's S. And then we'll do 360 minus each side. 360 minus 125 is 235. 360 minus 280 is 360 minus 315 is, calculate all that, and what do you get for the area of that triangle? 70,000.
451.
and that'd be square feet, we're talking here, right? And it might be that now, you could take this a step further, because I might ask you, let's say that land in this downtown area, is selling for about, $60 a square foot. Well, then how much should this businessman pay for that lot? It was $60 per square foot.
1,487,060.
Right, so you take the square footage and then multiply it by 60, and then whatever you get would be what that businessman should pay for that lot. Okay? It's a big lot. It's a very big lot. If it's a busy downtown location, then you would expect that it would probably be pretty expensive land.
Would you mind if I would take that round?
In the case of, if it were money, then I would say, yeah, you could round up to the nearest penny.
No, I mean like, when we're doing the square feet.
Leave it as 3 decimal places. Always, unless I tell you to round to the nearest foot, always round to 3 decimal places. Good habit to do.
I mean, that's it, but I'm talking about like when we purchase it.
No, leave the exact square footage and then multiply by 60 and then round to the nearest penny. All right. So that's Harris' formula, and I don't think that one's real difficult to work with. Next formula is, we're going to go through both of these, the length of an arc and then the area of a segment. And the first one we have is the length of an arc. Once again, I'll tell you what each of these variables in this formula represent. But the length of an intersected arc is S equals R theta, where S is the length of the arc, R is the radius of the circle, and then theta is the angle. But what's significant about that is the angle that's measured, it's got to be measured in radians. Okay, so if I give you an angle in degrees, then you have to convert that over into radians, which you know how to do. You'll just multiply by pi over 180. Now think about that Ferris wheel problem that we did a couple days ago. If you remember the stipulations of that particular problem, you had 36 different school buses around this Ferris wheel, and we determined that the length between these carts or whatever was 10 degrees. And it told you in this problem that the two carts were about 22 feet apart. Okay, so let's just say if we were going to take like the center of one to the center of the other, that was kind of where they came up with that value. But we know that's not exactly right, because if they're on this Ferris wheel, then they're really kind of part of a circle. And so, the distance between them might really kind of be thought of as that distance along this arc, as opposed to the straight line distance between them. Okay? Now for that problem, they wanted you to come up with a triangle, so that's why they gave you that straight line distance between. But really, when things are on a circle, if we want to measure the distance between those, or the length, then we really have to measure along that arc. Okay? For example, if you wanted to know what the length of a piece of pizza was. Now here's that very misshapen pizza, but pretend like it's a circle. And here's one slice of it. When we're finding the length, we're really finding the length along this arc. Well, a ruler won't help us with that, okay? Because it's a curved edge. So if we want to find the length of a curved edge, then this formula will find it for us. Our only other option might be to kind of lay like a piece of string along the edge, cut it so that it matches up exactly the crust, and then measure that piece of string. But what this does is it says that if you want to know what that length is along the arc, then you're going to, as long as you know the radius and you know this angle, that central angle, in radians, then you can find that length. Okay? And we'll look at an example or two of that in just a second. But the second formula is kind of closely tied to this, and that is the area of a second. Yeah, these are ones to memorize. We'll use these a little bit more frequently.
I don't think it's picking right.
All right, so for this formula, let's say we still have that same piece of pizza. Sorry if I'm making you hungry.
Yeah, absolutely.
Then S is still that length around the arc. R is the radius, and theta is the angle. What we're finding in this case, instead of the length around that curved edge, we're actually finding the area of that entire slice. And the area of that slice, again, it's not a perfect triangle, so we can't treat it as a triangle. Although the area of a triangle using this straight edge would probably be pretty close to the actual area of that slice. If we want the exact area of the slice, then this formula will give that to us. And that's 1/2 radius squared times theta, and again, theta has to be in radians. I'm just marking that area. Yeah, I'm okay with you going ahead and multiplying pi out. Now, if it's on the no calculator for the test, just leave it in terms of pi. But if it's on the calculator part, go ahead and multiply out. Yeah,
Was the last one in degrees, or was it radians too?
both have to be in radians. Okay, those angles both have to be in radians. All right, so let's just go through a couple of examples of these. These are not real difficult either.
It only becomes difficult if you don't have these.
All right, let's say that we want to find the length of an arc sometimes you'll hear this term that subtends a central angle of 72 degrees. So find the length of an arc that subtends a central angle of 72 degrees. So that just means that we have a circle and there's a central angle. That's an angle whose vertex is at the center of the circle. That angle measure is 72 degrees. Maybe give you some more information. In a circle of radius 10. 10 centimeters. Okay. And then the length of the arc that subtends that central angle, that's just this arc here that's formed by that angle intersecting the circle. So we want to find S. And what's the formula for finding the length of an arc? S equals R theta. Okay, well we know the radius is 10, but theta has to be in radians. So we're going to take 72 degrees, and to convert from degrees to radians, we multiply by pi over 180. So what do we get for that angle? 2/5 pi. And And so the length of that arc would be 4 pi centimeters, or rounded would be, what, 12 point?
12.56. So, two pi.
Yeah, if we convert that, it becomes 2 pi over 5, and then we plug it in.
Do you care which one that we're doing? Do you care which one that we're doing? Yeah.
This people's awesome.
All right, let's try this one. Let's say an arc of length 12 meters subtends a angle of 110 degrees. Find the area of the corresponding sector. And so we're given an arc length, and then we're told the angles measure that it subtends, and then we want to find the area of the corresponding sector. So, in terms of a diagram of this, there's a central angle of 110 degrees, and the arc length is 12 meters, and what we ultimately want to find is the area of this sector. Well, what's the formula for finding the area of the sector? 1/2 r squared theta. The problem is, based on the information that's given, we don't know the radius. What we know instead is the arc length, but we can use that. What's the formula for the length of an arc? S equals r theta. We know S is 12, and we know theta, 110 degrees, but I got to convert that into radians. So that's going to be 11 pi over 18. So I can use this formula to find the radius, and then once I know the radius, I can plug that in over here to calculate the area. As we know, theta is 11 pi over 18. So what do you get when you say 12 divided by parentheses 11 pi over 18? And then come over here and plug in 1/2 times 6.250 squared times 11 pi over 18, and that will give us the area of that sector. What do we get? And what are our units?
Oh, sorry, that's not it.
Okay.
30, 37.
Yeah, I could put some whole.
37 point.
497.
And what are our units? Meters squared, because we're talking about an area. That would be it. Alright. So you see, these formulas are fairly easy to use. So I'm good with that. So your homework will be from these two pages. And let me make sure that you want to do all of that.
Not really. It'd be fun.
Okay, let me make sure I want you to do all of that. 541. All right, 541.
What life?
That looks like that's going to be a lot of Heron's formula, which is good.
Great.
All right, and then page 365, that will have you using the length of an arc in the area of the sector. All right, yeah, so we'll do all this. So tomorrow what we're going to do is, after our class starter, we'll go over the homework on the law of cosines, which is what you had last night. Then we'll go over the this homework on arcs and intercepted and arcs and sectors. And then if you have any questions from the study guide, we'll go over those as well.
We're doing all these real quick.
Yeah.
Okay, so we didn't do.
So make sure you have all this ready to go over tomorrow in class. And then remember, your test is Friday. And if you are out for any portion of the class, then I've recorded everything and I'll be posting it up on the website in minutes. Hopefully soon.
Like this. I don't know.